Welcome, everybody. Thank you for signing up and coming to join us this afternoon to this virtual workshop. I know we're all pretty used to getting glued to Zoom all day long these days. We decided to keep this as 3 hours today and then some time tomorrow, so 2 hours tomorrow in a technical session and 2 hours in another technical session on the day after that, so Wednesday and Thursday. There's a break in the middle here, which is about 25 minutes. I think we'll be able to stick to that. In terms of participating, can I ask everyone, to the extent that let's try and do the following things. First, do try to use the hand up feature. So if you're, by now, most people are familiar with the various aspects and controls in their Zoom boxes. But if you're not, you go to the participants, and then down the bottom of the little box with the participants, you should see a thing that says hand up, hand down. And you can do that in order to ask questions. Feel free to jump in at any time. We want to try to be informal, but of course Zoom doesn't always make that very easy. Today, so to get started then with it, we've got this small slide that just sort of lays out the, actually I guess I should add one more thing, which is in terms of chat also, I think it's fine to use the Zoom group chat. We will be actually, and then another good thing to mention is we are recording the call. We intend to make that recording available. So if you do have concerns about that and don't want to be recorded in any manner in participation, I'm afraid we're going to ask you to just decide to leave, I guess, because we do want to make this available to others as they go. But similarly, the group chat is part of the recording, and we'll probably make that available as part of the recording. So just be aware of that as well. Okay, so SCiMMA, that's how we pronounce it. We just had a debate over Slack as to whether it was SCiMMA or SCiMMA. It is SCiMMA. This project is a project to set up a way in which we can develop cyber infrastructure for multi-messenger astrophysics. The workshop is aimed to bring together the multi-messenger astrophysics community, including astrophysicists, computer scientists, cyber infrastructure experts, data scientists. So we've thrown a wide net, as we have in our previous workshops. The goal here, by the way, of SCiMMA, it grew out of a workshop that was organized by the NSF to actually, sorry, Adam, I'll tell you if you want to.
Okay, sorry.
No, I'll tell you when to switch. So just go to the other, stay on the other slide for now, the community one. So slide 2.
Oh, sorry.
Yeah.
Okay, there we go.
Maybe I should drive.
Wait a minute. That is slide 2, target audience and goal for this workshop. That is slide 2. Do you mean slide 1, the introduction page?
I'm seeing the wrong one. I'm seeing slide 2 right now. So hang on, I'm not. I don't know what's going on.
The title of what I'm showing now is target audience and goal for this workshop.
Yes, yes,
yeah.
That's slide number 2.
Yeah.
Okay, good. Yeah, that's the one I want. Sorry about that. Okay. Yeah. So the one thing that I want to just mention is how this came to be. So there was a workshop organized nearly 2 years ago now. A group of us went and attended it. NSF was encouraging us to think about ways in which the multi-messenger astrophysics community could benefit from joining forces to develop the cyber infrastructure that is needed to do this science. And so we've been gradually growing the community since then. A group of us that didn't work together before started to work together across astronomy and astrophysics. but also we started to broaden that community to include computer scientists and data scientists, and we want to continue to extend that. So this workshop is now just to keep building on that and to tell you what we've been doing so far, and then hopefully to springboard off what we've been doing so far into broader community engagements and starting to actually explore using some prototype technologies that we've been developing. So do provide feedback, do ask questions, etc. The Google group that we have hasn't been very active, as you know, but we're going to start to make it a little more active. And in particular, each week we actually are holding, or each month we're holding an open telecon, so we'll be advertising that. The scope of the workshop today is going to have this introductory material. So we're going to give you the overview of SCiMMA, tell you kind of various things that we're thinking about in that area. We're going to introduce you to a few of the technologies and cyber infrastructure that we've been considering. In particular, we have been building out prototypes for an identity and access management architecture, and also for a messaging infrastructure, which we call Hopskotch. Those two are at a stage where we feel like we can demo them to begin to show you what we're thinking, but over the next 6 months, we really want to move them to something where we can explore their use and see to what extent they should be adopted as a production infrastructure going forward. Can we go to the next slide, Adam?
It should have come up now, isn't it? Is there a lag?
There is a lag. It's okay, I'll wait. There we go. All right. So in terms of this, there are actually 2 NSF awards that have been supporting SCiMMA so far. The one that is the most recent one is under the Harnessing the Data Revolution program at the NSF, which is one of the NSF's big ideas. And the title of the proposal is Framework for Data Intensive Discovery in Multi-Messenger Astrophysics. That is a 2-year award. It has 2 different components to it. The first one is these prototypes that we're going to talk about, and the second is working with the community to identify what's needed for the future, and then write down a plan that could actually be taken and used to get the NSF to provide funds to enable some of the program of work that the community thinks is desirable. So you can see down below, we've got the 3 goals for the period ending in September of this year. First is prototype some solutions that address immediate needs. Second is build and support multi-messenger astrophysics communities. And then the third is to begin a baseline design for an institute that would support multi-messenger astrophysics into the future. Next slide. All right, so one of the messages we want to convey right now is that we're not, we really want to make sure that people don't feel that there's sort of any, that we're trampling over what others are doing. The goal is not to do that. In actual fact, what we really are trying to do is think about ways in which there are technologies that can't be put together and made work by working as individuals, but that if we can work on them as a group, we can integrate them and then integrate the different projects that people are already doing. And there's a huge amount of other projects that are ongoing that we've had some discussions with people about, and others that we haven't. When you look at this diagram, it sort of sits in the middle, this Sustainable Cyber Infrastructure Institute to support multi-messenger astrophysics. And you can read the statement that's in there about what idea we had. And you notice it's got these linkages that go around to other items that we all know and love from doing our science on multi-messenger astrophysics. The thing that you'll see later today is we're going to discuss a little bit of machine learning in this session, this first session. But then after the break, we're going to come back and we're going to discuss brokers. And the brokers are one example of services and platforms that are being developed by others, and who that are trying to use data in different ways. And so again, what we see is that we can integrate and help with bringing certain technologies to bear on those rather than actually developing or supplanting them. That's not our goal. So I think with that, I'm going to hand over to Adam to actually, let me check. I have my participant list up. If anyone does want to ask, we could take a couple of questions about the organizational structure of things now if anyone wants. But otherwise, we'll hand over to Adam to talk a little bit about the more technical aspects of today.
Okay, thanks, Patrick. So, as Patrick said, the two sort of key cyber infrastructure components that we have prototyped furthest, and that we now want to open up to the community, are the identity and access management, which with which you may be familiar, or you're certainly familiar with it, whether or not you've heard it called that. Allows basically the controlling of access to data and services for users, but also users who are applications. And this is federated, so you can use your own institutional identity from almost any institution. You don't need to form 1, 2, 3, 4, 5 extra logons and then try and remember the passwords, and then all the pain and suffering associated with that. And then we have this this publish subscribe service, which we call Hopskotch. There's two perhaps rather trivial bullets there, but publishers send message to Hopskotch, and if you've subscribed to various topics, you will receive messages that have been published to those topics. You'll be familiar with other systems that have the same sort of functionality, like for example GCN, and it will be the case of the things with which you're familiar, like GCN. Those will be legal communications through Hopskotch as well, as will ATEL and so on. So the goal here is that with these and other applications, we enable this ecosystem of multi-messenger applications, which would include an analysis platform for incoming data, for example. You'll hear a bit about that later on. And tools for allowing the coordination of follow-up observations. One of the original motivating use cases at the initial workshop from which the whole of SCiMMA arose, that Patrick mentioned, was the mad scramble to follow up a LIGO event 2017, which was fantastically exciting, but it's not sort of duplicable to the event rates that we're expecting. There was a potentially great deal of inefficiency and overlap that people would like to remove. But so the target and observation manager software will help with that. That's largely being developed by people at Las Cumbres Observatory and other places, and we're working with them so that it can integrate into this Hopskotch SCiMMA ecosystem. Okay, next slide. So the first component there, identity and access management, we all know, even before the era when none of us could leave our house and go to work, we all know that distributed teams are a reality in modern science, because the expertise is necessarily rather spread out in most cases. And if you want to operate an environment where some things need to be secured and some things need to be open, which is nearly all of us, then you need trusted digital identities in the first place. You have to be able to identify people. That's the authentication part. And so certainly when I entered this field in 2005, and I'm sure other people can give their own perspective on this, you ended up with this gigantic patchwork of ad hoc logons, nearly all of which converged to having the same password. And it made life pretty difficult, because to execute one part of workflow, you would need a whole bunch of different logons. Okay, so the SCiMMA identity and access management system uses modern technologies, with which you may be familiar in other forms. You see something similar when you're invited to log in with your Facebook or Google account, including EduGain federated identity, and our platforms are hosted under contract at cilogon.org. And one of the leaders of the CI Logon project project, Jim Basney, along with SCiMMA's Warren Anderson, will be talking and leading you through this at the technical session tomorrow. Okay, so the features and functionalities here are basically implied by what I said. You can give access to resources to the people who need to have them. Okay? And the flip side of that is you can ensure that only the people that should have access to those can. And those are not a simple converse to each other. You can create collaborations of users, and this is really important because it allows you not to have some, you don't have to have a very permanent sort of structure. You can spin up collaborations. And this is also another sort of technology that will be enabled by the TOMs I was speaking about earlier on. And you can incorporate this identity and access management into your own applications going forward. This is sort of a thing, we're visualizing an institute going forward. This is one of the things that will be more properly achieved by an institute because it does require a certain amount of work and ongoing maintenance. All right, so here's some of the components in this sort of Hopskotch ecosystem, and you can get an idea of which way the data flows into and out of Hopskotch. Don't be confused by the fact, say for example, there's no direct line going from the TOMS / scheduler box to the query system to the archive. But to avoid it becoming a spaghetti of sort of massive spaghetti of arrows, we've just picked the arrows primarily going into and out of Hopskotch. Plus, this query system here will be accessing the archive. Now, the archive will be the archive of everything that's gone through the Hopskotch system. This will be analogous to, say, GraceDB for LIGO alerts, but it will cover everything that's gone through the Hopskotch system. And that's important because although there is some buffering inside Hopskotch, it's not going to guarantee to hold every message that went through it forever. So if you want to know about historical messages to do analysis or confirmation, then you would query the archive. Obviously, the observatories are often going to be the sources of triggering events, but in practice, they're just a specific element of users because anybody can subscribe, and anybody who's authenticated and has passed, a certain made certain promises and certain criteria will be able to publish as well. And it won't be difficult to publish. I'm just saying that subscribing will basically be free. You can pull as much as you want, but if you're going to publish to the system and it's going to go to a lot of people, then there are going to be a few rules to obey. And then over there, yes, you'll see the analysis platform. You'll be hearing more about that from Niall Gaffney. Okay, so in a bit more detail, this essentially details some of those services there. We're going to be building on existing technology wherever we can and building collaborations with other like-minded groups inside and outside of multi-messenger astronomy and astrophysics. So the central technology is that pub subservice, and Rich Wolski from UCSB will be talking about that in the last session today. And we've also, from very early on, it's been a very non-negotiable goal of ours to provide a client library on which you can build, or you can just use it as it is, to actually access Hopskotch. So you won't have to write your own code even to be able to subscribe or publish from Hopskotch. Now, you can write your own client if you want. You can also build on our client and extend it, and that's the sort of thing that we'll be looking at in the technical session on Thursday. We'll be leading you through that process. Now, brokers give a finer grained control over the streams of information than the topics of the pub subsystem. And Gautham Narayan is going to talk later on about how that works and how it can be integrated with something like Hopskotch. And then the analysis platform will allow the deployment of advanced machine learning and other analysis technologies, algorithmic development, onto the message data that goes through Hopskotch, and also the information that's in the archive as well, because that query system is a public interface into which you can pass queries. And Niall will be talking about some of those possibilities, illustrating in terms of existing technology, not necessarily stuff that's already being or has been applied to multi-messenger astrophysics. Okay, extracting data from natural language, sorry. So for example, the GCM circulars are basically natural language communications. Analysis of time series data and the detection of anomalies. And these are topics actually that are shared beyond multi-messenger astrophysics. Those people who were at the Harnessing the Data Revolution PIs meeting a couple of weeks ago will have heard this from all different areas of sort of data-enabled science. Now, let's say how you can get involved. there's various levels of involvement. Now, as Patrick said, we're engaged in community consultation. We also want to keep the community informed and updated. And if you join that SCiMMA Google group, and many of you already did, because I'm sure that many of you got here because of the advertisement that was sent to the Google group. You can just go to scimma.org and click join there. And you should also please direct anybody that you know who hasn't already signed up, you think will be interested to there. As Patrick said, the first Tuesday of every month, and this will be announced by the Google group, we have a public telecon. And then you can also, if you wish, contribute to our public repositories, because basically all of the code development is happening in the open. As soon as it's passed the initial tests, we make the repositories public. So you can contribute to those through the normal sort of git fork and pull mechanism, and you can find us on GitHub at github.com/SCiMMA. You can collaborate with SCiMMA. Now, we've adopted Scrum with 2-week sprints for the development of Hopskotch, and if you would like to be involved in that, please do. Well, you can contact any of us, but specifically my email address there is at the bottom. That's the easier one to remember, brazier@cornell.edu. You can also abrazier@astro.cornell.edu is my historic one that some of you may already have. And the security policy team and the identity and access management team, they have a telecon every week on Monday, and you're also welcome to attend that. So please do get involved, and whatever the right level of involvement for you is. But even with the extra collaborating, we have been onboarding people into our Scrum, because obviously we've been spinning up as we've been hiring people, new software engineers have been coming along, and that has been working very well. So by all means, get involved, or students you have working with you may be involved, or may be interested in becoming involved. Okay, next. Okay, so we're developing our organization in part to reflect our growing scope. So now we have the HDR grant. We have a higher level of organization, and always implicit in our work has been what I'm going to read out word for word as the mission statement. We've been thinking about this for quite a while, and this is the current form. I'm not guaranteeing that it won't maybe change a little bit, so don't rush out and get it tattooed onto your body just yet. Soon. So the mission, and I will read this out, is to accelerate science by catalyzing the development of a data science ecosystem with the workforce, knowledge processes, and cyber infrastructure that enables multi-messenger astrophysics. So I think what you see there is that we see ourselves as catalyzing and enabling. It's not, the goal of SCiMMA is not to produce a whole bunch of cyber infrastructure so that we can all stand around and admire it. The goal is to produce cyber infrastructure that makes possible or easier things that are currently not possible or are difficult. And that way we will get to science quicker, and we will have better science. And that's our goal. And to that end, we have software engineers, cyber infrastructure experts, computer scientists, data scientists, and of course, physicists and astrophysicists. Now, on that link there on our website under the resources tab, you can see activity areas and associated white papers. Organizational management is the next one we're going to complete, and we'll be kicking it off at that June open meeting, which will be the first Tuesday in June at 3 p.m. Eastern, 2 p.m. Central, and noon Pacific. So please do come along and give us your input there. Yeah. Finally, we have a code of conduct. It's available on our website under the About tab. Many of the elements will be familiar to you from working in other collaborations, or that you may have seen other code of conduct. It's adapted in particular from Parcel and the Contributor Covenant for Open Source Projects. And if you should see or experience or hear of any abusive behavior or harassment or other undesirable behavior, please do report this to the SCiMMA Community Standards Committee, who you can reach at scimma-csc@uwm.edu. And that email address is also in the code of conduct on our website. Now, obviously, at the moment, we're in a virtual environment. These things still go on in the remote virtual environment. And as we move back to in-person meetings as well, we have to be particularly alert. So please do read that code of conduct, and remember that should you become aware of any of the prohibited conduct, please do contact the Community Standards Committee. Okay, so in general terms, the workshop overview is that today we're having the overview that we're just about to finish very shortly, and then we're going to discuss some of the key technologies, and that will include, because there are such a wide variety of expertise, these overviews will include some basic information that may be familiar to some of you and not to others, and then we'll get into more application-specific detail later on. So machine learning is the first, that'll be Niall, and then detail on brokers, Gautham, and general information about Hopskotch Pubs Hub and where you can use it outside of multi-messenger astrophysics even, which is a thing we obviously knew because these pub subsystems are used outside multi-messenger astrophysics, but it very quickly became apparent that the one we're developing has particular utility. And then tomorrow there's the first technical session, which will be hands-on with the identity and access management system. And then that'll be led by Jim Basney and Warren Anderson. And then on Thursday, we'll have the second technical session, which will be hands-on with the Hopskotch Pub subsystem, where we'll actually be developing, well, actually using Hopskotch and then extending our own client. And in attendance on that, that'll be led by Bryce Cousins and Shireen El Sayed, but attending that will be the whole of the Hopskotch technical development team. So we'll be there to answer your technical questions as well. So finally, I'm just going to, this is the same workshop schedule that we have on the website. So just so you get an idea of the timings, we have 8 minutes left here that we can take questions, or we can plunge ahead into machine learning applications. Then we have a break, and then we'll hear about brokers, and then about Hopskotch and other fields. And then tomorrow we pick up again at 3 Central, so 4 Eastern, and 1 Pacific. That's right. And it'll be the same timing on Thursday for the second technical session. So does anyone have any questions, or I'll hand back over to Patrick if you had anything you wanted to say in closing.
No, so I don't think I had anything. I think that was great. Thanks, Adam, for the summary of where we are. Are there any questions or things that people are thinking about or wondering about in terms of how we're trying to move this along? Okay, well, if not, we'll let's just, I think we can just jump on into the next session. I don't think we have to be too strict on the timing. Because,
oh no, it's like a best man speech at a wedding. I think no one ever complains they're too short.
Yeah, and I don't think people will be just joining for one specific thing. So I think we can just move on into the next presentation.
So I stopped sharing, Niall, so you should be good to go.
Should be good to go. So let me just boldly share the whole screen, which you should never do, but it tends to work better when I go full screen. All right. Oh, there it is.
And I'll just say I'll be keeping an eye on hand. So if people do have questions, just stick up your hand, and I will make Niall aware.
Please do. So let me just sort of as an introduction, I'm Niall Gaffney. I'm actually Director for Data Computing at the Texas Advanced Computing Center, which is one of the larger National Science Foundation compute facilities in the country. And I'd like to say myself as a recovering astronomer. Prior life, I was doing data systems and data processing at SCiMMA for Hubble and other missions in the Moskowski archive, and many of those products. So I've got a background in sort of cyber infrastructure around data and data analytics going back a while. And I've moved on to TAC to join with a bunch of people, including Wei Zhizhu and Zhao Zhang, who are here today. And I get the honors of presenting some of their works in other fields around machine learning that I think are applicable in what we're talking about here today. So just real quick, here's sort of the bumper sticker for TAC, but we are a big data facility and house about 17 different clusters in our center, and really work in every research field you can think of in science and engineering, but also in other areas where we're doing humanities and consuming Twitter fire hoses and other pieces like that. So we have a good background in a lot of the cyber infrastructure and technologies and streaming data and in sort of modern machine learning techniques, as well as what everybody sort of knows us for doing simulations of colliding black holes and all those sort of things. But I sort of wanted to start off with a little bit of an intro about what machine learning is. Because it's been on the hype curve for so long, I think a lot of people are, well, myself included, sick of hearing about it. But it's actually a very useful term. And so machine learning really is sort of logistic and regression fitting. There are various techniques for working with data in different forms in it. And at the heart of it right now, at the heart of also a lot of the hype is sort of the neural networks in deep learning. And all of these tools have become very useful recently in a lot of fields that don't have as good physics modeling as, say, astronomy does. But really, the point is that they've become powerful enough because the data that drive them are now rich enough to do things. And so the real question that people need to ask is, can the statistical models, which are essentially, very rich statistical models but don't have the physics in them, outperform in either speed or accuracy other prediction methods? And that's sort of key. And that's been one of the things that is hard to get across to people in some fields where there are physics models. The physics models are great for doing the analysis in the long term. But if what you need is something to tell you something within the next 2 seconds, running anything short of simple line fitting is probably out of the question. The other question you have to ask is, do you have enough good data to build good statistics? Garbage in, garbage out is always a problem. But then the other question that's sort of interesting with machine learning is it can be a useful tool to find those unknown unknowns. Whereas if what you're doing is simply, fitting something to known models, you can indeed miss a result just because you assume that it was fit well by the model that you were using. So the real hype in all of this came about in 2008 when in the financial area, people discovered that, yes, this sort of statistical model could outperform the other models that they had for doing things. And that's sort of bled over into, shopping, as we all know, but then really has picked up in a lot of fields that we've been working with to accelerate the discoveries that they have. Even though it really is just sort of advanced curve fitting, it's a lot of curves linked together in a lot of different ways, in ways that you can't do as a person. So I like to just sort of think of AI right now as being a consumer and producer of information or data. And so Hopskotch is this, if you will, scientific Twitter fire hose with 4 different types of data that will need to be worked with as we move along in the MMA realm. We'll be going through, the thousands of transient events that are coming from LSST. Sometimes these will be formatted in a very structured way. Sometimes these won't. GCNs are semi-structured in their format. And these are going to have a wide range of different things that are going to need to be followed up upon. And right now we can keep our head above water with sort of the current email everybody systems, but we're going to have to quickly get around that and start moving into a different era. Then there's also the evolving events with poorly but rapidly improving things like pointing. A LIGO event goes off, and if you're going and looking for the source of that, follow-ups need to be taken in minutes, if not seconds. And so those are the sort of areas where some of these tools being able to work faster than the physics-based tools will really be important. And then interpretation of follow-up observations to coordinate overall discovery through these events and make sure that information flows out so that people can consume that information and make further decisions based on that is going to be needed. And that's another area where a lot of these sort of automated AI techniques can help. And then the last one really comes from the fact that the richness of what we do in research comes from not just, you know, the tables and numbers and images, but the discussions and notes and publications and all of that linguistically structured, but not necessarily digitally structured so that we can use it. And those are very important pieces of all of this. And with the archive of all of the both events, but then any other comments or things that take place in the Hopskotch ecosystem, having that information and having it be consumable and actionable upon it is something that is important. And I'll show that in just a second in other fields where people are actually making some really good discoveries based on what they are able to glean from publications and other pieces. But the real point on all of these is that, you know, for what we're doing, either for the volume or the velocity, the two of the V's of big data, which is really a term that I'm glad is dead, humans can't be in either of these loops, but these applications can be. And so that's sort of the importance of why pushing these forward and coming and working with researchers on making them believable, understandable, and transparent, and having them work with the physics-based models that we already understand so that we don't have, you know, we've all overfit a plot. Anybody can do it, but, you know, being able to get out of the system more than necessarily we put in. So this has really become, you know, this was the older model and the new model for what observations are. I put this in here just to show that, you know, it started off with emails and GCNs, and then observatories went and did their schedule and they did quick looks, and the observers would then send out more emails and GCNs and all that sort of stuff. And then you go home with your data from the observatory and you teach yourself to be a better observer as well as get some publications out of that. And that cycle has worked for astrophysics for you know, quite some time. And really all we're talking about doing is sort of changing this, and instead of it having be a trained observer, having trained models, and those can be physics-based or they can be statistical-based. But then putting those into a system where, as we've called this sort of the analytics workbench, is going through and working with all of the different pieces that are coming into the Hopskotch system from some of these researchers and from brokers and from, you know, people that are participating in the projects, and still having that quick look sort of cycle there where we are able to action on new data very quickly, but then taking that data and improving the models over time. And so this is sort of a model in computer science that's called edge computing, where you probably need a large data center to do a lot of the training, because you don't want to have that data center sitting on a mountain in Chile or in Hawaii where power is expensive. You want to do that somewhere else. And so this is sort of the model that I think we're moving towards in astronomy. And I'll show some examples of how we're doing those things and some of the techniques and technologies that we're using. So I think I've talked to a bit of these, but we really are talking about, you know, being able to extract entities and parameters from text, from unstructured and semi-structured data to give that data more life in a digital environment. So being able to pull out all those tables and maybe be able to come up with a time series plot of things as they happen. Feature identification and classification systems are going to be important. We're going to have parts of that happening from the brokers themselves. You know, you don't just get a raw LSST feed. They will have some classification on that, but follow-ups and other things will sort of need to be worked with there. Event classifications to improve the notifications to get the right information to the right people. And those can often be things that evolve. And so you may want to bring somebody in later on. So being able to say, hey, what's going on here is important. Why don't we message or do you think we ought to send a message to a colleague or something along those lines? And then lastly, you know, follow-up observations and fast analysis of these. Perhaps not, you know, I mean, we've all done fast and dirty analysis at the dome, where, you know, you are squinting at a fairly noisy piece of data. Those are the sort of things that a lot of these techniques are also very good at. And so using it to do those sort of things. So I'm going to show, I'll skip over this slide. This is sort of a up and coming thing, what we're talking about here. But I guess I will say that a lot of these techniques and technologies are needed and are being used in other areas, from smart crops to smart cities. We're doing a synthetic biology project with multiple robotic labs around the country who are running all of the sort of wet lab sort of work. And it's a very similar workflow. So there's a lot of commonality amongst this and a lot of structure to this. And so doing that with groups that are oriented towards the larger science picture sort of makes sense, because we can bring in some tools, hopefully, that haven't been used before and use them in new and novel ways. So that's sort of what I'm going to be talking to, is some of these tools that we have in other areas. And hopefully that can get some people's thoughts moving forward on this, what they might want to see, other ideas about other capabilities or tools that would fit into this, or sort of what we're hoping to have a little discussion about at the end. So the first one that I have here, of the couple that I have, is this DIVE project. This is the Domain Informational Vocabulary Extraction System. And this is a project that Weizhi Zhu has been working on for many years, along with other colleagues at TAC. And it's a text-based information extraction system. It was developed initially for the American Society of Plant Biology and Grammarian, which are two large plant biology journals. And the idea was to be able to go through their, you know, large corpus of information, really, publications, and harvest all of that into a more common repository of information, if you will. So extracting biological entities and linking those together, maybe as vocabularies change or as new things are discovered, you know, the ability to then go across all that information and see what the entities are and have the linkages between them. And the real point here is to be able to infer new relationships between these entities, both temporally as well as the information around them. And so the structure of the text and other pieces in the articles around them that give them that linguistic meaning to us, you know, being able to use that to improve either recommendations or associations with other pieces of the corpus of information. It also allows for expert user curation of the extracted and inferred data. And that's a sort of a key point to this, because of course, this is not something in any field where the information in text doesn't change. You know, these are constantly changing sort of things. And so this would allows people to, as they're going through their article publications, to help improve the system. So there's a little bit of Mechanical Turk work here where people give back on this. It doesn't have to happen in real time, but it does allow for an evolution of the system. So this is sort of how DIVE has been integrated into those publication systems. They've been used with the historical data, but also it's now actually in the system of publication, the Article Express that they use, where we're all sort of familiar with that left-hand side of getting a paper published, which, you know, is always a lot of fun of going through the review process and making changes, improving all of that, and that's important. But as that's happening, DIVE is working in the background to also do the entity extraction and linkages to sort of help with getting that moving forward while the article's being published, and make sure that you know, the vocabulary is consistent, and make sure that, you know, it sort of, if you will, it's sort of a spell checker for some of this at some level, or grammar checker, only it's about the entities that are in there. And it allows you to improve on that. But the key point then is once the article is finally published, it can go through that DIVE system And the final entities can be extracted and curated in a rather large database, which includes information not just about the entities, but about the context in which they were found in the articles. Every good system's got a web-based front end these days. I still like command lines, but that's because I'm old. But there's a nice web-based interface here, which allows that sort of curation of information and allows the improvement of the system for users. The actual architecture, the way that this works is that the information comes in an XML file, which is article text, and then the meta information about the article. So maybe keywords and other pieces like that. And all of that can go then into the actual entity extraction, which is a combination of at this point, sort of 4 different areas, which is entity extraction. There's a domain ontology to sort of match, terms that are sort of curated, known naming conventions, and then publication standards within the articles themselves. And all of these can be used to pull those entities and understand sort of, where they fell. But then the next phase is the entity assessment, where a lot of the sort of natural language processing techniques can be used to add more information to not only what this entity is, but how it was being used in the article. And all that information can be viewed through the sort of the Dive Web front end, but then winds up in the curation database, which has all this information stored, not just about that these things were, but that they were there. And this is where in this area, we could also extend this beyond just entity extraction, but allow for value, perhaps error, unit extraction. Most of those things are fairly easy to parse out of the text. If it isn't, it's probably not very readable text to a human. So that's an extension that we could make on this Dive architecture, add that in here so that we can not only pull out Z or redshift or radial velocity, or you can tell I'm a former galaxy astronomer, but pull out all those pieces of information and link them in a common way so that, regardless of how the information comes into the system, we can normalize it and have it useful for other analysis to take place. Here's just sort of an example of how this might work with a GCN. This is a fairly simple GCN here, but you can see very quickly, by hand, I can go through and highlight sort of what different terms would probably be pulled out and where then, right ascension and declination falls. It even has the J2000 in there, which is nice because it's always good to know what, everybody should use J2000, but it's always nice to know what equinox your pointings are in. And it has other information such as links to FITS files and light curves and the sky map. And so FITS files will also have other information in that can be used. And so this could really be used as a way to pull information from these semi-structured, and I would count a FITS file as being a semi-structured entity. Yes, the keywords are 8 characters long, but that doesn't mean that it's well structured. But pull all that information together in some way to have this database of information. Well, it's great. You have a database of information. What do you do with it? Well, this is where some of the machine learning, the deep learning comes in. And working in this field, they have a very simple, what they call neuronal engine, which is just a 3-layer neural network. So a very simple neural network that goes through and can then build the inferences as well as understanding sort of what terms go with what and what articles might be related to what articles, which is an interesting feature because it's been used in other fields like material science, where people are actually discovering new materials based on this recommendation system that had never been associated with one another, simply because of how the recommendation system said, hey, this is a material, you might also be interested in this material, a la, Amazon, which used to have horrible recommendation systems and now actually has a pretty good one. So it really does give you the ability to go through and come up with this recommendation system. And just to sort of show how much better it is than just plain, throwing things into a Lucene engine or some of these other things, using full articles from Dive and other techniques to sort of do article recommendation. Narayan is able actually to come up with fairly good recommendations, so the precision of recommendation. And it gets even better once you start getting into not just entire articles, but into particular sections of articles. And in fact, small chunks of related words seem to really work well, is what these plots are showing, which is exactly what a GCN, what a lot of these notices are. And so this technique could be used, I think, very readily as a consumer of messages, as well as a producer of recommendations, and perhaps being able to tell the right people that they might be interested in this particular object. So it was designed as an extensible system that can incorporate additional methods, and that's really what we hope to be able to do here. It has both the capability to internally learn things as it discovers, but also to teach it, which is key to all of this, and helps us do these recommendations, which when you're going to have tens of thousands of streams coming in a night, having a recommendation filter, hopefully better than your email filter, keeping the spam out of your inbox, working for you, is going to be sort of key moving forward. So that's one thing that we want to be able to do, is working with those and come up with recommendation systems, as well as value extraction, so that we can work with those inside the science platform, rather than having to go sift through things and do it the old-fashioned way. The next project I want to talk to is this, what I'm calling deep learning-based time series change analyses, which also here in Austin we call bad traffic. So this is an example of another piece of sort of edge computing, or potential edge computing, where we're able to take the streams of videos from some of the cameras on the light posts and stoplights around town, and go through and identify objects in them. Now, this is not a real, you look at this at first and think, well, that's great, you know, cars and people, but this isn't how astronomy works. We don't actually go through and identify hundreds of moving objects in a single frame. But it does show that sort of there is the ability to do time series sort of analyses. You could think of each of these frames as maybe being, you know, they could even be objective prism or grism type spectra. There are different forms of data. They could be spectral data, or they could be the raw image data where you actually are looking for moving pieces. But the key is that this is going to be an area where the training of this model happens somewhere centrally located, because you don't want to do that, you know, sitting out on a hot street corner. And then you push those models out to the light posts or wherever else the cameras are to sort of do the extraction. In this case, the goal here is to not keep the video, to just keep the database of the cars, people, and buses to be able to do incident reporting. So it really is sort of looking for a different kind of event. And so these are all capabilities, these are that exist with a lot of the sort of deep learning imaging areas. And really, deep learning doesn't care whether it's an image or a spectrum. It's a vector of numbers in its heart, and it's doing fitting to it. So there's a lot of things that can be done with that, but it turns it into a much more actionable area. And so this is sort of doing feature detection. And then once you have feature detection, you can start looking at, you know, what those features were doing, how they were moving. But the real key then is that you can do sort of anomaly detection. And so this was a particular area, actually just up the road from me here in Austin, but they were studying sort of the behavior of pedestrian traffic and how it interacted with the traffic going up and down the road as they turned on this crosswalk here, and went through the data and saw a lot of these sort of other features. But then there was this weird little prehensile tail that came out that nobody was expecting, because, you know, why would you wander up and down the middle of the road like that? And so this feature was brought out by the fact that the entities had been extracted and cataloged and then analyzed, and they were able to then go back to the actual video to find out what this was. And it was somebody delivering cars to the Subaru dealership over to the left there. And here he is wandering out, and you, in fact, you know, this is the we missed the terrifying moment of the truck veering past him. Here's the next almost collision caused by all of this. And so it's this anomaly detection that also is important in working with machine learning applications, which is really sort of key. It's how it can be set aside from, if you had a simple model for how that intersection should behave, you never would have discovered that that truck was there. And in fact, they're trying to change and put in physical barriers so that trucks can't park in the middle of the street and do things like that now. So those are the sort of key features that we have current applications going here at TAC. We've got many others that are sort of around this edge-based evaluation, whether it's remote sensors or other pieces. And really is sort of very similar to what we're talking about doing here in Hopskotch, is having, a stream of data coming in, being fast analyzed with no humans involved, and then better training as the situation improves. So edge-based computing is very important for what we're doing here at TAC, both in sort of the few astronomical projects that we have, but a lot of the other bio and ecological projects that are going on. Yeah, so we have applications going in that, and would be very interested to sort of talk to how those things could be used and where it would be practical to start experimenting with these things on existing data or existing data streams. And so with that, I was sort of planning to talk for 30 minutes here and then throw open for about 10. So we're running a little early. I will sort of open up the floor about either thoughts about what we have here or other ideas that might be good for us to pursue, or problems that you have that would be good to pursue that we may be able to look at solutions that we have in other areas to improve the outcome of what's going to happen with SCiMMA.
Aaron has his hand up.
Hi, can you hear me?
Just
Hello.
about. You're pretty faint, Aaron.
Let me try again. Can you hear me better now?
Yeah, that sounds good.
Thanks for this talk. It was very interesting. I wanted to bring up a concern, which is about the text extraction from the circulars. It seems, at least to me, that this, while archivally this might be useful, if we're really talking about building this whole new system, this is more of a band-aid on the problem than solving the problem. And the Fermi GCN circular that you showed is actually a great example, because although it is unstructured text, associated with that circular, there was actually a structured machine-readable notice that has all of the same information. And the tradition has been that circulars, which are these unformatted human-readable things, do not necessarily come with notices that contain the same information. But there's no reason why why we can't change the techniques of the community or the way the community interacts and say, okay, these human readable things are good, but they should always be accompanied by some machine parsable notice, which some people already do. And it seems to me that is a much better solution, or at least part solution. So
I could not agree more. Part of this is Moses to the mountain. It's often it's harder to get people to change their behavior is one thing. And so for the GCNs, I agree. I mean, I look at them with if you take your glasses off and stare at a GCN, you can see their structure, right? And so there's no reason why that can't be easily submitted with the structured information in some format.
So what I think.
Well, Adam, let me just throw one more thing in, which is though that when part of it is the creative element of all of this. And so if this becomes, and it hasn't been mentioned yet, but if this is a publication subscription system that includes the collaborative efforts of people acting during or around these events, often those pieces are just plain text discussions or thoughts and comments. And so, that's where sort of, I don't want to do, it's not like we want to go through and do sentiment analysis on this, but this is where a lot of the techniques may come up that can help us with the recommendation system around those text pieces, where, you know, discussions seem similar to other discussions, or, you know, surfacing those discussions to remind people that those things have happened. So it can be both forward-looking and backward-looking in a real situation like that. So I think there will always be some room for the text part. As far as the RA and DEC go, yes, give that to me in a nice JSON document, and I'm happy.
Yeah, I fully agree with you. I just think that we could probably get a significant fraction of the way there by, you know, if, you know, again, as you said, it's a Moses to the mountain problem, but
yeah.
I think that there are people that are willing to buy in and have sort of, not just because it hasn't been the norm and have been tied to technologies that make it a little difficult to do so in the past, but there's no reason that that has to continue to be the case.
Absolutely. And the notion of semi-structured as opposed to, dare I say, you know, some of the virtual observatory things. Yeah, there are some scars as well, I think. So you wanted to add something, Adam?
Yeah, so all I was going to say just quickly before we go to Leo is that we discussed this at a meeting last September. We've adopted a dual approach. You're absolutely right. We picked out the potential to to use machine learning essentially to help guide people, write things that are much more much easier to pass, and sort of behavioral changes as well, like Aaron was talking about, where you send send a circular, but so there's a notice too. But also we didn't want to create a system and then say it's only going to work if everyone changes the way they behave. So it was always the goal that our system, that the existing communications that people use would be legal in the system, and then we would hope to change the way that people use the system for the good over time, rather than saying, here's a brand new system, if you only use it this way, it'll be great, otherwise it won't work. So it is a difficult decision, and astronomy is riven through with these sort of historical behaviors that are very hard to change. And
different funding agencies.
Oh, yes. Yeah, absolutely.
Yeah, and focusing on a mission versus the overall ecosystem. And I'd like to say I would hope that that's what we're going to try and foster out of this as a center, is to, we're not going to force people to do it, but hopefully show them the light and hope it catches on in a way that isn't specific to one mission or to hopefully even just one particular area of astrophysics.
Yeah, multi-messenger astrophysics is a good way to do it. I see Leo has his hand up. You're muted, Leo.
Have you thought about whether there's a place for, sort of embedding semi-machine readable vocabulary into circulars? I'm sort of imagining like sort of embedding Twitter-style hashtags so that you can easily recognize whether a GCN, for example, is reporting a spectrum or if it's reporting photometry, or is that something that's that would help in per meeting, or is it just not necessary these days?
Well, I'll sort of look at this two ways. One is controlled vocabularies are what every library science and data curation person strives for. And the problem is they don't work because you can't really control vocabularies, and some things are just different. And some people might, hashtag spectra, hashtag spectrum. So, now you're extracting and you have to make linkages on those already. So it may be best to allow, especially in a system like this, the discovery of those linkages, so that if hopefully things are happening even in other languages, they could be brought in. That's a long stretch there, but I don't know if we want to have, hashtag supernova, hashtag boom. mean something.
If I
Probably
could
easier
jump,
just to write supernova.
if I could jump in for a minute, Leo, I think I think these types of ideas are the types of things we've on occasion brainstormed around ourselves in the small group that's been going so far. But I think that I think there's path forward here. So I think it'd be great to pursue it. Hashtags, I don't think in specific, that example hadn't been mentioned. A thing that we were thinking could be done is sort of a crazy idea, but a fun project on the sort of data science side was, sometimes when people are formatting, especially the circulars, there's a lack of precision, what exact type of calibrations used, various details like that, what filters mean and so on, maybe missed. But if you imagined an autocorrect service for Google that could work with good examples and basically suggest, hey, you forgot your units here, or things like this. That's another way that we could actually improve it and actually make the data much more easily extractable by having this sort of suggested way of writing things. I personally think there's just a fun, creative set of things that could be played with here. And I think it'd be great to get anyone who's interested to start to chit chat about it, maybe try a few projects and bootstrap up a broad collaborative program. Be fantastic.
Yeah, and so, we've got some of the technical expertise behind that, but having the domain people drive that, even though, I haven't done astronomy in decades, I've just built systems, but, having the domain experts help with that and work together, those are the sort of projects that we'd like to get going and would like to talk to in the coming month, and hopefully get something, as we're, correct me if I'm wrong, Patrick, but having, a demo of something by the fall of some piece of this service working against things would really be a feather in our cap in showing that the community is coming together to do this.
Yeah, and I think not only that, I think the question to some extent is even just the working together. So if because our goal is really to bring some more resources to this whole effort by trying to get people working together and getting things done. So if people want to jump in, I think it'd be just fantastic, to look at this, play around with it, and see what we can do to make life better. Yeah. I think I always say it the way I've said it before. I think, Leo, you'd identify with this. I know others do. Is that sort of if you look back at GW 170817, there were PhD students who basically, got their PhD because they spent their time indexing and extracting all of the information out of the GCN circulars in order to be able to do analysis and follow up and investigate. And it would be nice if we didn't have to have them do that by hand. They could actually do it either by having structured information come, as Aaron said, but I think it's more likely by having both. So having both the structured information and otherwise.
And I'll just say, storage and compute should not be a hindrance on this. We have that. We just need people and time, which is always the hardest thing to come by in all of this. So I would, maybe even, I'm just sort of spitballing here, Patrick, maybe even creating a system that could just reproduce one of those, I won't say PhDs, but the extractions might be a good demonstration of this working. All right, is there anybody else, Adam? I'm still in full screen.
So I see Josh has his hand up.
Yes, so what you're talking about building here is an enabling technology, but I guess I didn't hear, apart from the conversation in the last couple of minutes, what the kind of home run science activity could be with this enabling technology. And is there just one, or are you envisioning a bunch of different use cases on top of it? I think we all certainly agree this is needed as sort of a middleware on top of the raw data stream. But I think it'd be useful as you start building out your demo to have a semi-aha moment that you couldn't have gotten by other means, or you can get it much more fast because this technology exists.
Right. Well, I think that one of those is that, the extraction information that I was just talking about, showing that can be done real time rather than over the course of 3 or 4 years.
But that's not the science, right? So the question
No,
is,
I understand. But then when it's assembled in a way that people can look at and do the science with, that would be one thing. The stretch goal would be, yes. I mean, everybody wants it to just publish the paper for them. That is the goal of AI, I think, is to just, get the researcher to get their H score up. But it's not, there are other pieces to this. And so the other parts of this would be, how rapidly can we react and help refine, a potential kilonova or something along those lines. I think, there are the two different use cases of one is the, fast and furious, lots of notifications coming and putting those together on a particular object. But then there's the unique event use case where you're going to want to get all the information and the right information in front of people at the right time to make the decisions that they need to make in order to get the follow-ups going. And that may be more than just an error or ellipse on the sky.
right, but I think, and I agree with that. I guess I just asked the question more broadly. If you're thinking about recommendation engines for, this event is like this event, or if you like this event, you'll love these past ones.
Right.
What's the? I guess I don't see what the science is in that. And it's okay to say, well, it's okay because it's just a enabling tool for exploration and potential discovery, but I think it can be made sharper, and in the time that you have can help focus the actual work that you do, if there is a North Star around a specific science that is enabled because of that. Because exploration is fine, and being able to do deep dives as a human much more quickly over lots of different data that you wouldn't otherwise been able to do is great, but it's just not the science endpoint.
I agree with that in that sense. And I also don't know how much, I love the examples of there's some in biology as well, where I think it was cancer treatment and oysters came together through some weird match of machine learning DNA. These associations that happen that, occasionally may spark an aha moment. These aren't science. They really aren't. But they are enabling science that probably wouldn't have happened otherwise. And so I think that's, it's a wishy-washy answer, but I think that's what it's doing. And if that's not important, or if that's not something that folks want to do, that's cool. Not a problem. But it would be, it would be interesting to see where it goes. I've sort of chased this idea around for decades, and it hasn't caught on for the same reason.
But we do want to hear from you what it is that you can't do at the moment.
Yeah.
This is something that we've been trying to establish in the early SCiMMA meetings, is that, normally as scientists, we want to report our successes, and obviously that's an important part of science, but we're not always as clear about what we can't currently do. And we would really like to hear from the community, what can't you currently do?
So, and Josh, you might have missed some of what was said there, but it's not just recommending like, oh, if you like this circular, here's another one. It's extracting all relevant information about a given transient to put it all in one place, which currently does not exist. So, right now, if you're interested in some, GW event, there's associated gamma ray bursts, and there's, 5 dozen telescopes that have similar data. And there's something in NED that you want to know about these different galaxies. There's a Glade Galaxy Catalog. People have plans to do this other thing. All this information is scattered all over, dozens of sources. And so one of the goals here is to read like these just word blobs that people send out about it and associate everything together to make it so that it enables science much faster. So the real driver science-wise is that now, in the crucial first minutes after one of these events, you can be on Sky and doing something and coordinating with a bunch of people, you know, in a matter of minutes, as opposed to the 5 hours it might take, you know, at the moment. And so then you can get those early observations that will allow you to decide between different models for what's going on that we just can't do right now because it takes too long.
Yeah, I mean, I totally get that, Andy, and thanks for the clarification. I'm thinking even maybe a little bit broader and trying to learn some of the lessons from the VO, which built a bunch of middleware of a lot of, it'd be nice to have, without any killer apps on top of that middleware.
Well,
And I think we should try as a community to both build the infrastructure that we all know is needed, like what you just described well, Andy, but with some clear endpoints in mind. And again, I think it's fine if the endpoint is let's just enable people to work faster and pull data in an associative way across lots of disparate data. That's a fine endpoint, but we should be clear that that's the endpoint that we're working towards and not some other type of that's enabled with.
Yeah, all right. There's maybe we gave these presentations out of order, but and this has come up in Aaron's question as well, and I think people don't really have yet the full picture of what we're trying to do in SCiMMA. We really are building this backbone of communications infrastructure that will go much farther than the way that people communicate now. And one is just, you know, TNS, GCNs, ATELs, all these things. We're making something that's incorporates all of that, but it also has machine readable components and has these kinds of tools for things that aren't machine readable. And we're trying to make collaboration and communication tools for astronomers that will build on things like the treasure map and the TOM toolkit that LCO is doing to enable, like, you know, machine readable, faster communication between observatories, between users, share data more quickly and effectively, and so on. So this is just one tiny subcomponent of a much bigger infrastructure picture here that we're doing. It's just that some of this stuff is not, you know, it's not all assembled together yet, and so we can't do demos of it. But we do have a roadmap going forward for how to very effectively, and completely unlike the VO, we're not trying to solve a generalized case. We are trying to solve a very specific case of how do we enable people who want to follow up gravitational wave events and other multi-messenger things. How do we make that quicker and far more efficient and decrease repetition and redundant, you know, people doing the same thing and everything else like that.
And if I can, I swore I wasn't going to beat on the VO until somebody else did, so now I can. I was at the first VO meeting, and it was a very different entity than what's going on here. I attended many VO meetings, worked with Bob Hanisch on this, and saw the whole thing have its, you know, become what it became. I'll just say that. And, you know, this is why we want to have this be a community institute and not, you know, a board deciding what will solve all of astronomy's problems. So these were meant as examples. I would love to hear other things. If people have end goals that they want to try and work with, let's talk to those as well and see what we can come up with.
Yeah, I agree. I think Patrick has some to say, and then we'll close this session and go to break.
Yeah, actually, what I want to just say about this is I agree with all the perspectives that were said. I think Josh's point of having a killer app. So one of the things I think we all have in mind is that we should make sure we're not just building technology to have technology. On the other hand, part of just the programmatics of how we're funded does require us to kind of look at innovative algorithms within the context of data science. And so this is more what right now I would say we have this notion that this can be a very enabling technology, but what we have to get started on is to bootstrap it up, study it, get the community involved to look at how it's working, and then decide, has it gone the right direction and is now a useful tool that actually does enable some great science? Or is it something that should just be set aside with a nice little paper that documents why we set it aside? So the goal here is, like Adam mentioned earlier, we've adopted Scrum and sprints for development. Well, to some extent, we want to actually also try and take a similar approach within the context of building an institute. Do some sprints on technologies, on approaches, on ideas, and if they come to an end, just then move on to something else. So I think this is, I think machine learning is clearly something we might want. We really want to find out where the uses are, and there are definitely places. It's just finding the right ones. Over.
Okay, cool. So I think we should thank Niall. That was really good. Thanks, and very thought-provoking. And if we reconvene at 45 minutes past the hour, I think that's the schedule. And then we can go into the last two sessions of today. So the Zoom will stay open, so you can stay logged in as you wish. And in 19 minutes, we'll start again. Okay, so I think we'll be starting in a few seconds. It's about brokers and SCiMMA. Gautham Narayan, who I guess you're the lead developer on Antares, Gautham?
I lead the algorithms development, but I'm not the lead developer of the actual system.
And an assistant professor at the University of Illinois, Urbana-Champaign. So I'll hand over to you, brokers and SCiMMA, and you've got 45 minutes. I
won't try to use all of that. So thank you, Adam. As he mentioned, I'm a professor at the University of Illinois and part of the Antares team, but I also have a third hat that I'll be wearing and switching on and off today, which is that I am one of the co-conveners of the LSST Supernova Working Group within the Dark Energy Science Collaboration, and that's the group that's particularly interested in multi-messenger astrophysics, particularly since we are hoping to use kilinovae and other events, for example, as standard candles down the line. Okay, so if you look at this cute little graphic that I have here, this is kind of setting the stage for what a broker is actually doing. If you see somewhere in the center, there are some graphical representation of a MMA event like GW170817, and those things are being observed, those events are being observed by a whole bunch of different facilities, which are collecting data individually about these events. And so what a broker does in some sense is try to sort of make sense of an alert stream of those things. So not one of those events, but an entire ecosystem of those events coming in from a large facility like, say, LSST. So this is the LSST view of brokers. They will be taking postage stamps of images from images every single night, generating alerts from them, distributing them to the community through these broker systems. LSST by itself won't tell you if a particular alert is, say, a supernova or a kilonova or a variable star or whatever that is. But it will have some kind of simple filtering service for you to, say, scan the properties of a given alert and find the things. But that is, of course, not what most of us actually do when we're trying to find transient and variable sources in real surveys. What we are usually trying to do is sort of given some light curve of an event, we're trying to sort of annotate it and collect all of the other information that's available, as Andy mentioned in the discussion during the last talk. We're trying to sort of characterize that event, classify it if we can, and then make some kind of prioritized list to what's interesting for actual follow-up. And the LSST filtering service doesn't do any of that by default. And so these community brokers are really trying to step in to this space and provide the services that we currently try to do with optical surveys that have been going on, such as ZTF and PANSTARS. I want to also have you remember this picture for a second, and I'll tab back to Adam's image of Hopskotch to show you that Hopskotch and this picture are actually not all that different. This messaging system that's in red in the Kafka queue is in fact exactly how Hopskotch is being implemented right now. And so while this bottom diagram from LSST is talking about all of time domain science and how to characterize this development of Hopskotch for the MMA community has a broader use and can be used by a larger group than simply folks who are interested in multi-messenger astrophysics. Okay, so brokers then are services that receive the alert stream, try to annotate it by cross-matching against other catalogs, for example, and deriving features, as Neil mentioned. We're trying to use those features to sort of, as inputs to machine learning algorithms to say, classify the alerts or the light curves. And then you actually have to rank them and prioritize them and distribute them to a community. So you need some kind of filter service to sort out what alerts people actually want. And those can be completely different use cases determined by the actual observer. And then we want to send them some kind of substream of alerts. You can imagine that users or observers have a particular watch list for alerts for their favorite objects. Is, for example, if you happen to know that something is a recurrent nova, maybe you want to know when it's going into outburst. And you also want some kind of integration with follow-up observation services. So something like the LCO network that Andy, for example, is a part of. So what brokers exist? Well, I'm, of course, part of this Antares team. And so Antares is effectively the first thing I'm going to tell you about. We are already live and working on ZTF, and we let you sort of manage the ZTF alert stream. We add contextual information and characterize these events and do all of this ranking and distributing that I just talked about. But critically, some of the features that we sort of do have right now is that you can write your own filters, essentially bits of Python code that run on the alert stream and allow you to identify alerts that meet your criteria. So you can do your science on ZTF already. And the goal, of course, is to, in the MMA context, correlate optical alerts from surveys like ZTF or LSST in the future with, say, gravitational wave signals from LIGO, high energy particle and neutrino triggers, such as things that you might get from, say, Swift or IceCube. And this is where we plug into the multi-messenger astrophysics ecosystem. And this entire system is live now. You can use it. The URL hasn't been updated to say Niall Lab, but the entire system is ready to use. We are not at all the only broker. LSST ran a community broker workshop last year. And so with my desk hat on, I have to sort of maintain a list of what brokers are available and what the capabilities are. Because DES is really interested not in developing its own broker, but rather working with an existing broker team. And we expect many, many people to actually sort of use brokers in this fashion, even big groups, rather than sort of develop their own system from scratch. It makes a lot of sense to sort of use an existing broker that's being developed. Some of these are older than others and consequently have had much more development. Others are currently conceptual and haven't actually gotten any traction with the community yet because they don't really exist. But there's a whole lot out there for you to choose from. They have different capabilities. Many of these things implement the same capabilities in different ways. And so you already have your pick of these systems and can sort of choose what you want to do based on your own preference. Okay, so Josh had asked the question of what sort of science can you do with these things, or is it just something that enables science without actually doing stuff itself? And so LSST, which is the sort of context in which I think about brokers, because that's going to be the biggest game in town and it produces 10 million alerts every single night, has 4 primary science drivers. And largely they can be split into these 4 categories. So there's groups that want to understand the nature of dark matter and dark energy using transient and variable events such as supernovae, for example. But we're also interested in detecting things like strongly lensed supernovae. We're interested in sort of understanding quasar variability. We're interested in finding kilonovae, sort of at lower redshifts, if you like, nearer to home. We are, of course, very interested in sort of sorting out what potentially hazardous asteroids there are, making a catalog of all of the solar system objects that there are. There are groups that are interested in how the Milky Way formed. If, for example, there were merger events in the past of the Milky Way that has led to streams of stars, for example, moving from one galaxy to the other, can we identify those variable stars, for example? Often there's some tie-in between the science that you can do there and studying, say, dark matter. And of course, there's a whole bunch of people that are interested in sort of the demographics and population of the transient sky. What are groups of objects out there? What are their progenitor systems? How are they forming? What sort of impact do they have on, say, nucleosynthesis? Kilonovae, for example, might tell us a lot about our process nucleosynthesis. And so we really want to study populations of objects in their own right. And brokers are really trying to sort of enable all of these 4 science cases. And so I'll step through a little bit and show you how that might work. So if you look at the sort of variable sky, it's a zoo. There's a whole bunch of decisions that one has to make when you get an alert. Is it even a real object or is it some artifact from a difference image pipeline? If it is real, is it transient or variable? What kind of variable it is? What kind of energy scale it is? And so this is a multi-class, multi-label classification problem. And so brokers are really trying to do this using machine learning tools, replacing what people have historically tried to do by eye. So right now for existing surveys, many people get alerts like this and sort of make these decisions visually, coming down this tree effectively and deciding what objects meet their science criteria and merit follow-up entirely visually. So not all of those objects on that tree are equivalent, and you'll see that the vast majority of alert use cases will fall into sort of 3 big categories. People are really interested in transients, and particular special kinds of transients. So supernovae, objects like kilonovae, GRBs and such. There's a group that's interested, of course, in the population and demographics of variable stars and such in the Milky Way. And then there are folks that are interested in sort of longer period variables on the night sky. And so things like AGN, for example, that don't just rise up and fade away. So brokers are really trying to enable these sort of science cases. And so one way of thinking about common transients is there's so many of them, they're not all going to get follow-up. For example, type 1a supernovae, well, if you can identify those reasonably, you don't necessarily have to go take a spectrum of every single one. And of course, a group like DESC, which I'm a part of, wants to identify hundreds of thousands of these things to do cosmology. So occasionally we might have a night or two on a facility like, say, Foremost or LCO, or maybe a classically scheduled night. And you'd want some kind of filter that can run and find objects of interest that are rising or near maximum at that time, that you can follow up at the telescope when you want it, but you don't necessarily need to worry too much about, say, having a constant stream of these things identified in real time with minute latency or something of that nature. There are, of course, situations in which you might be worried about really common objects on absolutely short time scales. So for example, potential solar system objects are things that we'd like to flag as soon as possible to, say, have some advance warning of another Chelyabinsk, for example. And we're already, of course, doing this with the ZTF stream and a team at the Northern Arizona University. We can have a filter that sort of works on streaked sources and identifies known solar system objects that we send off to them, and they can sort of use those objects effectively as a downstream broker and decide how they want to react. There are, of course, longer timescale transients that don't require any kind of immediate response. And so for those sort of things, we have a sort of search system where you have a giant database, Cassandra database of all of the alerts. And you can write your filters to identify these sources. Within those databases, you can write very complex filters, actually, because the entire system that's currently implemented is Elasticsearch. So any criteria, any feature at all, either in the alert packet from ZTF or derived by the broker itself, can be used to write a big query. And so sort of more specifically, for example, we can identify things like AGN and tidal disruption events. These can be identified by, say, where they are, location in the galaxy, are they near the nucleus or not. We have catalogs of data to help distinguish AGN for TD. For example, we have a catalog from Decker French, who's another professor starting at the University of Illinois, and Ann Zabeldoff at the University of Arizona, that has a list of potential TD host galaxies. And so every time you get an alert, you can cross-match against that. And hopefully that gives you a little bit of extra information to distinguish between AGN and TD. And of course, you have a watch list of objects. You actually have push notifications to this from Slack. If you like, you can configure your filter with your Slack username, and it will send you a little message every time your particular watch list of object has an alert. You can also do this for all of the alerts in a given filter, though I don't really suggest that unless you want to have 10,000 Slack messages and your Slack client going ding, ding, ding every 30 seconds. Brokers really also enable searching for new objects. If you look at the sort of discovery space in terms of luminosity and characteristic timescale, you can see that there's this big white area on the left-hand side of this plot. And we expect surveys to discover objects in this region. It's just that current surveys haven't really been sensitive to these particular length and magnitude scales. And so they've not been populated. In fact, if you look at this plot carefully, you'll notice there's not even the kilonova actually on here. And we have only one of those examples. So can we find more of these things on the night sky? Can we identify characteristics of their entire population? And of course, if we can eliminate populations that we do know and understand well, then we'll have a better chance of finding the things that are outliers, anomalies, if you like. And so this is actually kind of where multi-messenger astrophysics comes in. Antares, for example, already retrieves LIGO sky maps as the minute they're pushed out, the LAL inference maps, for example. And any alerts that are within that sky map, within a particular region of that sky map, and within a particular separation in time, we sort of automatically start to flag and follow up. We can make a list of all of the host galaxies in that region and prioritize which ones might have, which ones are more likely to have so electromagnetic counterparts for, say, binary neutron stars or neutron star black hole systems. And so the goal of doing something like that is really that you want to get the sky map very quickly. You want to sort of identify the electromagnetic counterpart. You want to schedule follow-up so that we can do studies of these objects, these very rare objects in real time. And this is really the core mission of SCiMMA, but this is also a core driving science case for brokers. And this is sort of showing you that entire process in a really beautiful graphic from Las Cumbres. Okay, so how do brokers actually do this stuff? Most broker systems, I told you there are a bunch of different ones, but most broker systems will look largely similar to each other. They all have some kind of messaging subsystem, if you like, to take in alerts from, say, a survey like ZTF or LSST. And then within the broker itself, they have a large database of existing catalogs and also previous alerts. They sort of cross-match that alert against any previous history at that location, and then run a bunch of filters on them in real time to sort of annotate, characterize, classify, and then output that to particular users based on the filters that they define, or in other words, that you define. And that output can be in the form of a web interface, but there's also a API client if you prefer, and if you really want, you can get things like notifications on your cell phone. And then, of course, entire systems to sort of monitor the entire process in real time. So the sort of first stage that we do is add contextual information. And if you look at the night sky over the last 50 odd years, you'll find that our holdings of data catalogs have just increased absolutely exponentially. You'll notice here that DES has just turned on, and you see the familiar DES tank down in the bottom right there. And right now we have essentially coverage for most of the night sky in existing catalogs across multiple wavelengths. And so we can cross-match in the optical, but also add near-infrared data. We can look in Chandra and Veron. There's just an absolute ton of information that's currently all over the place that brokers are trying to put in one single location for you to access. And at that point, once you have all of these features effectively, you can start to sort of use machine learning to sort of identify and characterize them. And so the sort of very first thing we do is begin with a large imbalanced multi-class training set that we've sort of built a pipeline on. There are simple filters that we can use to trigger rapid follow-up. For example, if a source has risen by, say, 2 magnitudes or something like that, we want to know straight away. And we can do all of the things that you heard described in Niall's talk. We extract a bunch of features. Many of the simple features that we extract are sort of well-known and come from work from Joey Richards and Josh Bloom's group back in 2011. This is sort of the classic paper on that. And we're now using, they were used to classify full light curves in literature, but we're now using them on streaming data, and they still work really, really well in this particular context. We can also do really more expensive processes once we have a lot of information on a particular object. So for example, we can run Gaussian process regression to model all the light curves. That helps you distinguish different kinds of variable stars from each other, variable stars from supernovae, etc. And so if you're looking for, say, final classifications for a big output catalog made, say, annually or something like that, we can do that. We've done things like wavelet decomposition. So if you take a smooth light curve, say from something like a supernova, you can break that into a bunch of square wavelets. And then you don't need the actual light curve. You can simply work off of the coefficients of those wavelets, which is effectively data compression on the right. You don't need all of them. You can live with just the first few. The first few might give you a rather blocky representation of that supernova, but that's actually still enough to classify things fairly effectively. And of course, as Niall mentioned, we are no strangers to using neural networks for classification, for example. So I had a student, Daniel Muthukrishna, who has built a recurrent neural network using gated recurrent units to classify a bunch of different classes of variables and transients, shown here on the right, some of the examples of some of them. These are light curves that were simulated in sort of an idealized ZTF cadence in ZTF's own bands that we use as the training set. The training set was essentially built off of the LSST plastic challenge, for those of you that may have taken part in that. And this thing seems to work pretty well. We've used it to sort of identify supernova in real time. So those are ZTF alerts coming in. And you can sort of see, as you get more and more alerts, the classifier becomes more and more confident that this particular object belongs to a specific class, in this case, a time disruption event. So I've given you sort of an overview of how things work. Oh, I should also actually add a little bit about the host classification. So we're no longer just interested in, say, associating things with a host galaxy for annotating a node. We're actually interested in using, say, postage stamps of the host galaxy to improve our classification, using contextual data effectively to do better than we have been able to do in the past. And so that means that for every single alert, we actually have to decide if it's not just a transient or a variable, but if it's a transient, see that we can find an extragalactic host if it is indeed extragalactic. And so we've been building a really large database of all known supernovae and their host galaxies, their types of transients, their redshifts, photometric redshifts, host galaxy features, and we can use just the host galaxy information without any morphology of the light curve at all to sort of classify these things to roughly 70% as is. And so this is work that my student Alex Galliano is writing up that should be out pretty soon. And this is really helpful for something like, say, SCiMMA, because early on, if we're trying to follow multi-messenger sources, we don't usually have a lot of optical observations. The object's really, really faint. But what we have instead is a prior of where it is on the sky from, say, LIGO, and potential host information for galaxies in that sky map. So it's really the galaxies that are going to tell us what the transient is likely to be. And people have already been doing this sort of by hand, effectively deriving lists of likely host galaxies for a given transient and then scheduling follow-up observations. But there's space here to do this with machine learning. Okay, so I will bravely try to show you some actual demonstrations of some of this stuff. So if you've been following Archive, you'll notice that there is a fun recent new object called AT2019 DSG, which has a high energy neutrino coincident with a tidal disruption event. And just to show you how little data there is right now that you can easily find in a centralized location, here's the object's entry on the transient name server. It does something about the redshift, gives you a spectrum, but you can't, scanning this, find anything about this neutrino detection or really get a light curve or anything of that sort at all. You can get some postage stamps, you can query a few other services for catalogs, but you actually have to manually click on a button to go there. And this is where the broker comes in. So this is the view of the broker for the same exact object. You get the light curve, you get all of the alerts from that particular light curve, you can drill down into those particular alerts, but you also get all of the catalog matches that we've associated this particular object with. If you want to find a chart, you can get one. You can even sort of customize it and decide whether you want what color bands you want, for example, in that, if you're an observer at, say, the telescope. You'll notice that this has a couple of annotations. So it went into an output stream called Astro Rapid, which is that rapid algorithm that I just told you about. And Rapid has currently identified this as a TDE. This is a nuclear transient. And you can get this sort of web view, but of course you don't have to get a web view for it. If you prefer to sort of have API level access, you can sort of get, for example, all the catalog matches or any of the information on this particular object as a JSON, just with a simple API call if you have the alert ID. And so you can drive down and see in every single one of those catalogs what information there is in one place, rather than sort of doing this with a whole bunch of different services. And this, of course, works not just through a web interface. If you really want to do this through a pipeline, say in Python, you can do that. So I've listed a little catalog query as just a JSON file. There's nothing else in this directory, but I can quickly run a query on this particular object with an antares. It's some ZTF source for which I have a ZTF name. This will take a second or two to get the information, but you can see that's pretty quick. In real time, there should now be a file called output.json, which I can quickly cat into JQ. And you'll see there's a ton of information here from this source, from the broker, all in real time. That entire Python call is a Python package that we make available to you. And so you don't have to write any code. There's a library that you can incorporate into your pipeline if you'd like, or just use the client directly. And it gives you all of the information. It tells you what streams that alert went into. So essentially how we annotated it, this particular objects, for example, I've annotated with something that says this locus has 2 or more detections, as in DESI brightness name. So we're triggering on that for DESI, which is a spectroscopic survey that's running on the Kitt Peak 4 meter. And so this is one way that you can do things, but you should also be able to write your own queries to sort of enable your own science. So to do that, we sort of are going to go to the NOAO Data Lab. I haven't even logged into the system really. I'm going to launch a Jupyter notebook, which is running on Data Lab's own servers. You can sign in. I've done a bunch of filter development for interesting sources. So for example, we can take a look at a simple filter like I showed you in the slideshow, but we can also look at much more complicated filters. So this is what actually happens for the LIGO filter. We get sky maps, for example, that Antares caches. You can determine which alerts are nearby in time. You can determine whether these alerts are actually plausible, and do a really lot of complex filtering to sort of decide whether this object is realistic or not, whether the event's false alarm rate, for example, is too low. Anything that you really like that comes from either LIGO or from ZTF or any of the other optical surveys we care about, you can write as Python code. And when you're done with writing that code, you simply go into Antares and say add, and copy and paste it in the little window. And because I'm an admin, you can sort of see a whole bunch of Python codes that people have written, including people on this call. So Danny Milisavich, who I saw signed in earlier, for example, has a particular alert or a particular filter here called refit new sources, SNR cut v2, which is a very descriptive name. There's checks for against TDEs. There's a whole bunch of different things that one can do in here. We're also sort of doing processing of Ogle alerts now to find microlensing sources, for example. We're serving other surveys such as the Young Supernova Experiment in DESI with alerts that match their own criteria. And people can, of course, update these alert criteria over time. And different surveys can have multiple people contributing alert criteria if they like. And of course, all of this client stuff has documentation, so you can be up and running today with the system. It really enables a lot of the science that we've talked about so far. And so this is cute versions of stuff that I'm going to skip over that should sort of show you that we could do all of these features. But I'll pick up here, which is to say that the division between brokers and the pub subsystem is a bit fuzzy. They're both subscribing to messages from observatories. They're both publishing messages to downstream users or TOMs or science platforms. And both of them have some kind of query system. So there's clearly places here that they can work together and maximize interaction, minimize redundant development. And the reason this sort of works, I think, is because brokers are really trying to address what information the community wants from the alert stream. Take one alert and find everything that you can about it. Whereas, and that sort of, in my mind, I break it into these 4 steps of annotation, characterization, classification, and prioritization for you. But pub subsystems are really trying to address how the information is shared between different users. And that sort of brings me to sort of my wrap-up slides, which is how we can connect brokers with SCiMMA. So brokers would love to have a single unified way to connect to alert streams from different observatories. We ideally wouldn't like to develop this individually for, say, AMON or IceCube and LSST and ZTF, each of which have different schema. So we'd really like to replace GCNs and ATELs and DNS and all of these Kafka streams with one single pub subsystem to rule them all. This would be ideal because it just sort of is not really what we want to be doing, is developing communication protocols between different observatories. And this is a larger scope than just MMA, because we're really talking about doing this for all of time domain science. But MMA is definitely a major beneficiary of this work. If we can also stop having to worry about how we interface with, say, the observatories, if we can offload, say, the interfacing with DOMs to, say, a system like Hopskotch, then we don't have to spend developer time on building that functionality. And we really get a better follow-up ecosystem because everything is plugged in to one single system. And so this is effectively what you've seen with services like TreasureMap that are sort of presaging what you could do if you had a single common interface. And Hopskotch gains from all of this as well. Hopskotch doesn't need a backend database to store all public alerts that are sent out by observatories. The broker's already doing that. But identity and access management is going to be a major issue. You can imagine, for example, doing follow-up on, say, Kilonova source, and in the next few years, that's going to be really, really important and interesting, and people are simply not going to want to share that they found something interesting in, say, a particular galaxy. And so there is an entire layer of, say, extending identity management, which you get with, say, ORCID even, with how to actually do access management. And this is, I think, where an MMA institute that's funded can have a lot of sway and sort of effectively govern how this process works. So I'll end here and end with sort of asking you with what do you want brokers to do and how do you want brokers to sort of serve the MMA community better, and sort of take any feedback you have.
So I see Andy Howell has his hand raised.
Yeah, one clarification to what you said there is you said replace ATALs, GC, and so on. Our usual statement is that we are supporting all of them, and but we may provide additional functionality that moves beyond what they're capable of right now. So, you know, our friends who are making these other tools, we're not trying to say we're trying to eliminate you. We're trying to say that this is a
no, and I think I made this point myself in the chat. I've used ATALs and GCN, and I still do, in fact, very regularly. We're not talking about short-term, we're getting rid of these services. There's an entire adoption by the community that has to happen as well. But long-term, we do need something for big surveys like LSST that we have to recognize that services like ATAL and GCN can't provide. That's not to say that the work that has gone into them is not absolutely heroic.
Yes, this is a somewhat political statement, but the point is we're not trying to antagonize anybody here. What we're trying to do is provide much needed tools that are not currently available to the community to go beyond what we can do now. And we'll make those tools open. So that's the end of what I'm trying to say.
The place was very, very poor there. I admit I'm sorry, but I do sort of think about it on a 10-year time scale.
Yeah, okay. That was one thing I wanted to say. Another thing was just that yeah, the line between brokers and toms and Hopskotch and everything can get a little bit blurred, but to some extent, you know, some of these we just want to make a focus tool to do one task. So sometimes, you know, brokers are quite a big all-purpose utility, as are toms. There are some areas where they can overlap and do one thing. So you said we don't need a database for Hopskotch, but we are making a database for Hopskotch, and that is to enable a public user interface to browse the alert streams, and so that there will be a user interface to be able to look at Hopskotch stuff that's available to the community. We'll try to make it plug into the Tom toolkit. To some extent that overlaps with what brokers do, but it is more of a single focus. Just do this one thing, and then, you know, if you want to then take pieces of that and roll it into your own Tom or whatever you can, but we'll provide a community version of that.
So the charts that Adam gave me was, how do you think about brokers connecting with SCiMMA and interfacing better with them? How can we onboard brokers? And so my goal here is to sort of minimize any kind of redundant development. And I think that having groups like, say, the team developing Hopskotch, having regular monthly meetings with the broker teams can lead to a lot of sharing of technology, which, as Mario put, the underlying technology is really quite the same. And so we can save a whole bunch of effort and get to this idealized ecosystem for multi-measure astrophysics much more quickly if we work together. That's what.
And I think actually, I mean, if you have two databases, but some of the effort, because they have a common spine, and a lot of the effort that went into producing them has been shared, then actually the waste is not that big. But what I would say about the database for Hopskotch is that purely records the stuff that goes through Hopskotch. So unless, say, a broker fed back through Hopskotch some of the results of the algorithmic filtering work you do, then that would not be in the Hopskotch database. Of course, if a broker did that algorithmic filtering work and fed it back through Hopskotch to send to people, then it would be.
In fact, that's exactly what I'm imagining is that we not only subscribe to services like Hopskotch to get alerts from different facilities, but we also push the results back to the same service.
Right, and that will be. I mean, that's how we envision it too. I mean, it's not. People are free to choose how they wish to subscribe and publish, but I think that's the best situation. The question I had for you, you know, in terms of what can brokers do for the community, I wonder what the criterion are for deciding which filters you will implement and which you won't.
It turns out that the filter codes aren't really a huge amount of overhead, and often they are asking for the same sort of features over and over again. And so for the time being, we think we can actually run most filters, and that's okay. And we might work with filter authors to sort of, if somebody wants G minus R color at 12 days and another person wants G minus R at 15 days, maybe they can both live with G minus R at 13 and a half days or something like that. And that way we can sort of run all of these filters. And that's more or less the plan for most of the current brokers. In fact, with my desk hat on, we sent them a questionnaire earlier this month asking them what their capabilities are. And most brokers are open to running any code you give them. Not all of them have this functionality quite yet, but they certainly are expecting to get there by the time LSST turns on.
Okay, and I guess your overarching requirement then is that you can manage the throughput, so you can process 1 day's worth of events in 1 day, or some sort of 1 hour in 1 hour, or something like that.
Right. For Antares especially, the goal has always been doing all of the processing in real time, which means we have about 40 seconds once the alerts come in.
Okay, so a fixed latency.
Fixed latency, yep. But you can also imagine that if for some reason, say you're pointing at the galactic plane and you suddenly get vastly more alerts, you can throttle how many you process, and then when you have some spare cycles during the daytime, then you can process the remaining that you didn't process at night and send things out then. And for most science cases, I don't think you need such high latency that 40 seconds is too little, but you could probably live with, say, 5 minutes.
Okay, and the absolute worst case would be 12 hours of data has to be processed in 24 hours, so you're ready to go the next day.
Yep. And a lot of us are thinking about redundant systems, for example. So, for example, if a cluster goes down, can we move some of the processing to, say, AWS or Google for a short period of time and get results?
Right, yeah, and then you'll have to know the processing cost, because that turns into actual money cost.
Yep. So LSST is going to be doing a broker test. It was supposed to happen this year, but has been moved, I think, to early next year because of the COVID lockdown. That'll, I think, answer the question of how much time it takes to process alerts at LSST scale for all of the broker teams, but also for the project. This will all, of course, inform what brokers the project chooses, but will also give broker teams some real answers as to where the bottlenecks in the system are at LSST scale. And we're doing some of this, of course, with ZTF right now, but ZTF is between 1% and 10% of LSST.
Right. Yeah. It's a different game altogether. Okay. Does anyone else have any questions for Gautham? Thanks very much for that, Gautham. That was really illuminating, and also finished on time too. Thanks to everyone actually for getting done on time. Okay. So next up, and to finish off today's session, is Rich Wolski from the University of California, Santa Barbara. Rich is a computer scientist, has done many things, but has a particular expertise and experience in building robust systems that run in the cloud. And he's going to talk about Hopskotch and how it can be used in general.
Hi, everybody. Yes, thank you very much for sticking around for the last talk of the session. I promise to be brief. And let me see if I can do my screen sharing thing here. All right, let's see. Let's share that. And then I have to do this. And then let's see that. Okay, hopefully you can see that.
Yep.
Right, so I want to apologize. I know almost nothing about multi-messenger astrophysics. My background is I'm a computer science professor. I understand and work in cloud computing, both commercial and on the academic side. And I've done a lot with high performance distributed computing in Exceed, the NSF centers, this kind of thing. So, so it's a real privilege to work with this group and to learn about how hard scientists use large-scale systems, distributed systems, to do new science. But you know, my perspective on it is purely technological. So I learned a lot of new terms today, like Kilonova, excellent. I don't know what one of those are, but they will not appear in this talk. So what I wanted to do though is maybe provide a technologist perspective on what's happening, or what I believe, or what I've come to believe is happening as a result of participating in this project for some time now. And that is that in this multi-messenger astrophysics space, there's a real need, as Gautham was saying, to have a component that can do pub/sub. And you know, what a lot of knowledgeable astronomers are saying is, oh, you know, it's kind of fuzzy as to what pub/sub is and what pub/sub isn't. From a technology perspective, it's not fuzzy at all. And that's because on the cloud side of things, where we're doing web services that are trying to sell you things, you know, the lines between you know, front end and database and filters and queries and so on and so forth have been drawn, and they're pretty bright. So so part of what I'm hoping to do is kind of illuminate what those lines look like on that side of the fence, and then we can talk about how that might benefit this community, right? So pub/sub is for streaming data, yes. But it's actually, you know, it's actually very stylized. Each stream is associated with a topic. Topic is typically a string. It doesn't have to be, but it typically is. Publishers append events to that topic that are described in some canonical format. And subscribers ask the system, which is also typically called a broker, but a different kind of broker than the one that we just heard about, for access to the stream based on topic. So it's, I mean, it's very, very rigid. In addition, there are certain services that these pub/sub systems typically offer. First off, there's a quality of service. And most pub/sub systems support best effort, which is you'll get the message at most once. Sometimes there can be message duplication, but you know, the communication system will try and deliver a particular event in a stream if it can, at most one time, at least once. So it's guaranteed to make it there into your stream, but it might make it there multiple times and exactly once, which is where the, you know, some sort of reliability mechanism is kicked in and it's done duplicate suppression or something of that nature. And these come with different performance characteristics. They come with really different reliability characteristics and tolerance for things like outages. So typically in the pub/sub space, you have to think carefully about what quality of service you want and what those trade-offs are like. Pub/sub systems also present this event stream, and there's usually some configurable amount of finite history. And the history is presented in terms of the order that events come through the stream, and order is an issue that we can talk about. It's not the order that the events are presented to the system. It's some order that all consumers of the stream are guaranteed to get with the better pub/sub systems. But a common misconception is that that the delivery order is in some way related to the arrival order, and that isn't necessarily true, although you'd like it to be true. Other things that pub/sub systems typically do is callbacks. So instead of querying, which is a typical database operation, these pub/sub systems will notify you, send notifications when certain kinds of events have happened or when events arrive. That's the filtering thing that we were hearing about. But typically you connect a filter with something, you know, be it an email, an SMS, another message, or another event that you wish to generate. They do often support queries across streams. So you can build these filters. Sometimes it's called a streaming database, but it's again based on topic and an event. You know, so there are SQL-like things that are trying to do that rationalization. And they're usually built to scale with subscribers on the commercial side of things. the theory is that there's a small number of publishers, but a large number of subscribers. That's not always true. It doesn't have to be true. But when we think about this in the cloud space, that's generally the model. Okay, so what does this have to do with Hopskotch? Hopskotch 0.x, the initial version that we've been working on since the first of the year, is based on Kafka. And Kafka is a distributed open source message queue system. Message queues were originally designed to support multi-tier web services. So when your load balancer vectors a web request to one of the web servers, it can use a message queue to get that request there. The message queues then can be interposed between sort of web server processing and your database. They're persistent. They're usually very, very high throughput. This particular one was developed by LinkedIn. And then there's a layer on top of it that supports this topic-based pub/sub mode of operation. It's very, very high throughput, and it's fault tolerant, which means that the data is internally replicated. If you lose servers that are serving your data, the system will stay up, highly available. The choice for Hopskotch was really driven by LSST, which we just heard about, and that should say ZTF, sorry. There have been some good experiences and some software engineering practices that are particular to MMA that seem to make sense. So we thought, okay, we're going to adopt Kafka both for its commercial utility, and it is by far the leading reliable message system for cloud-based web services today. It supplanted RabbitMQ a number of years ago. It's got an active development community, et cetera, et cetera, et cetera. So some thoughts on pub/sub. Pub/sub is streaming, QoS enabled, keyed by topic, and a message delivery mechanism. It's not a bunch of things. It's not a relational database. It's not a NoSQL database. It's not a time series database. It's not an eventually consistent object store. And it's not a causally or temporally ordered event system. And the reason I say that is because in the computer science space, we see people building all of those things on the bottom half of that slide using Kafka, and they shouldn't be. And so the computer science view of this is, you've got a way to do this topic subscription consumption mechanism. It's got some really good performance characteristics. It's got some really good durability characteristics. That comes up a lot, the ability to move these events from one place to another, to put them in databases, to put them in other brokers that are trying to amalgamate information, to generate alerts from them. That functionality comes up a lot. And so the idea behind Hopskotch is to build a system that has sort of an agnostic API with respect to the technology, but then take best of breed technologies from the open source community, bury them underneath that ABI, and then do the engineering necessary to make that super easy to consume, okay? If you want to do this in the cloud, and the reason I say that, you might think, why wouldn't you do this in the cloud? And the answer, I'll give you that answer here in a second. But if you want to do this in the cloud, it's throughput and subscriber scalable, it's distributed. And what this means is it can leverage scale out. You can add separate virtual machines to the pub/sub infrastructure, and you get more of something, either more durability or more performance or lower latency. It's fault tolerant and highly available and data durable, which means that if you lose everything, you can restart the system and the data, and particularly in your histories, is still there. So those features are all present in Kafka, but when we think about pub/sub systems just for cloud-based applications, these are the properties that we're trying to engineer in, okay? And just to give you, thanks to Mario, a quick use case, this is what he sent me for ZTF. Each night is published as a separate topic. There are 7 days of history available. It does 600,000 to 1.2 million alerts a night. And the alert sizes are between 60 kilobytes and 70 gigabytes each. His team has benchmarked it at 80,000 alerts per minute. So that gives you some idea of the throughput thing. And this is all done in 4 gigabytes on one instance of AWS with 2 virtual CPUs. That's amazing, right? That kind of throughput with this kind of load in that one tiny little package. I mean, it's cheap, but it's also remarkable that so little resource can do that much. So that's what makes the technology so attractive. In terms of subscriber scale, it's not that big. This feeds Antares, apparently. I want to say, I hope that's right. And it's about 6 to 10 streams. Kafka can do much more than that, but this is the current sort of use case, or one of the use cases that we discussed when we decided to adopt Kafka as the basis for Hopskotch. So Hopskotch is technology independent. It's a client and server interface, infrastructure, whatever you want to call it, for MMA pub sub. The client is currently written in Python. And this is for a bunch of reasons. One, it's super easy to integrate with a lot of the tools that astronomers use. The last talk we saw Jupyter notebooks, and we heard about Python filters, and it looks like the alerting system's written in Python. This is kind of the coin of the realm at the moment. So this client is compatible with that. The server side, the thing that runs the pub sub mechanism though, while it has Python wrappers, it's containerized so that it can be deployed easily and effectively in cloud environments and in other environments, which I'll talk about here in a second. It's IAM integrated. So you can do this, but if you want this to be something that's got curated access control and identity management integrated with it, that takes some work. The interfaces are there, but you'd like that to be sort of separate from the underlying technology as well. And then there's a great deal of work that's going into code, rigorous code management. So in the open source way of thinking of things, packaging so that it can be easily consumed, and developer support, QA. We're using an agile software engineering mechanism or a development process. This is if you haven't heard of this, this is sort of the way things are done with web services today: continuous integration, continuous deployment, CI/CD, these kinds of tools that are really used on the commercial cloud side. Today, the client installs with the standard, or a couple of the standard Python package installers, so pip and conda. The server actually has a bunch of deployment scripts for AWS. It's container-based. And so in theory, this is easy to consume. This is something that isn't like Amazon, where there's this army of people behind the scenes who are managing it 24/7 and whose beepers go off. You can take this system and either put a team behind it or use it for other processes, right? Other kinds of science, other applications. It's open source, cloud-based pub sub. So to give you an idea of what other applications you might use it for, this is something that actually sprung out of another collaboration that's in our group. We work with a bunch of people who are using Internet of Things technologies to improve agricultural processes, sustainability, and ecology. This is completely separate from our SCiMMA work. And as part of that effort, we've got a number of different projects. This is a picture of one of them. This is a citrus orchard in Visalia, California. And if you look in the center of the picture, across the reservoir, about a kilometer, you'll see a fan. Okay, that fan is used to prevent frost. When it gets cold in this region, and this is just up against the Sierras in the Central Valley of California, the cold air float goes to the bottom, warm air about 30 feet up, and that's about the height of that tower is there. And if you can mix that air, you can actually prevent the frost from freezing near the base of the trees. So those fans they're usually propane driven, sometimes they're gasoline, They turn them on. They have to turn them on 6 hours before a hard freeze. It's tremendously expensive. This particular orchard spends $50,000 a night to prevent frost. It's dangerous. There's a crew that has to circulate at night, high labor cost, huge carbon footprint associated with this. And what they would like to do is build a system that puts sensors into this environment, figures out what the temperature gradient is, makes some assessment about how much before hard freeze, based on time of day and when the sun's coming up and other atmospheric conditions, about when to turn the fan on and then when to turn it back off again. So, so what we've done is we've instrumented this space with a bunch of very, very low power devices. Now, it's important to understand, we can't go and put a supercomputer out there. In fact, we don't have electrical power out there. This picture is taken from the nearest place where there's reliable electrical power. It's about a click from that fan. So what we do is we go out with these devices that have various sensors put on them, and we put them in the orchard. Except the orchard is a place where industrial activities are taking place. They're driving tractors, sprayers, so on and so forth. You can't put up big solar panels and not interfere with this. You can't trench for conduit. It's expensive even. So all of this has to be done in this very, very sort of low invasive, non-intrusive way, which means low power radios, very, very low power devices so that you can survive the night on a daily battery charge with a small solar panel. These things then communicate to other low power devices, which are remotely located with larger solar panels and bigger batteries, that eventually hits an outbuilding where there's actual reliable power. We put a small cloud, that on-farm edge cloud is a bunch of Intel NUCs running something that is like an Amazon knockoff. Over on the left-hand side, we're actually integrating with a bunch of other scientific instruments. That thing is called a flux tower. It's measuring the CO2 flux through the soil. It's also near a burn pile. Charcoal is pretty high in CO2. Amazing. Probably didn't need to measure that, but they are. And so we're gathering all that information to try and do this frost prevention thing. And the key thing that's important to understand from this perspective is everything on the left side of that blue bar is incredibly unreliable. It goes down all the time. We have to put in tremendous amount of redundancy. When it rains, things stop. Sometimes they come back, sometimes they don't. And this is really different than on the right side, where we think of doing a lot of the processing. AWS, Google Cloud Platform, Aristotle, NSF Campus Cloud effort. These things are so much more reliable than the things we're trying to use to do some of these activities, that you really have to be very careful about data durability, about where the data flow is, and so on and so forth. Okay, so along about halfway through the Hopskotch effort, we started designing a monitoring system for those very, very unreliable devices. And we actually built one. And it was built by graduate students who were in the biggest hurry to leave and leave behind whatever it is that they say is working as quickly as possible. It became pretty clear that our monitoring system was no more reliable than the devices it was monitoring. We said, okay, we're going to do this for real. And at the end of the day, we wound up with a Hopskotch architecture. We wound up with something that looked like a deployment mechanism for the server that was scripted and automated, could run anywhere. A set of client libraries written in Python that could be easily ported to different, environments. There's a little bit of weirdness here. We need a transition event. The telemetry is showing up periodically all the time. And we're looking for a transition. We're looking for a dead spot, a period of silence. So there's a little bit of processing. So those are, so what we want is something that allows all the devices to publish, and we notice when they stop publishing. And then that generates an alert. And then the subscribers are graduate students, which means no email. Email is not cool. You never want to email a recruiter at Google. You want to SMS them or Slack them or WhatsApp them or Twitch them or whatever. So we need a way to interface the alerts to the constituency in a way that the constituency can consume. And for sure, it isn't a website and it isn't email. So that's phase one. We wanted to build this system. We kicked it off. Shireen, who is the developer on this project, built it in 4 hours, which is just amazing. I mean, it took me longer to put together the slides than it took her to build this thing. So this is a good argument for why you want to do this with professionals and think through it. Okay. So phase one is, how do we use Hopskotch and this Kafka thing to do this pub sub? But there's more, right? As soon as we got done with that, or Shireen got done with that and went off and had a cup of coffee while I tried to write it up, we started thinking about this and said, well, you know, our devices really shouldn't proxy to this. We should really have pub sub for IoT. Problem is, there's tens of kilobytes of memory in these things. Maybe you have a megabyte of flash. They're solar powered by day, battery powered by night, and they run on a duty cycle, which means that they go to sleep most of the time. This is not Kafka. Kafka will not run in this environment. It is not duty cycle friendly. It is way too resource intensive. You can't get Python to run on these things. Forget about, you know, all the persistent stuff. And so, you know, a lot of what's built into Kafka assumes the right-hand side of that reliability graph, cloud level reliability. So today we broker this, but in the future, what we want to do is bury pub sub underneath Hopskotch. So there are pub sub things for these low power resource restricted devices. One such thing is Mosquito SN, MQTT SN. We're looking at that as a potential port for the Hopskotch API. We also have our own in-house distributed hash table implementation, which looks way more robust and also duty cycle friendly than MQTT-SN, and we can argue about the computer science behind that. But that's a PhD thesis for somebody in the computer science area in the space. So already, you know, this is driving new research because we're going to compare these two approaches. And so phase two of this project will be to do this skinning of some pub sub technology with Hopskotch. And then phase three is to integrate that with Kafka so that you get this end-to-end, you know, pub sub infrastructure, which is for IoT. That's a long way from MMA astrophysics. It really is. But at some level, what we believe is that these applications where you have many, many different data streams that have to inform either, you know, decision support or actuation. We're going to turn the fans on or whatever. This is a common theme. And so if we can leverage this engineering effort to make it so that these things can be easily consumed, you get a number of benefits. It's portable, deployable. You know, we can run it anywhere. We can run it in an edge cloud. We can run it in the public clouds. The key thing that I think.
Interrupt, right?
Yeah.
Rich,
yeah.
Leo's got his hand up. Sorry.
Oh, please. Sorry. By all means.
No, it's sort of a high level question. You can wait until the end.
Okay. Sorry about that. I didn't have my thing up. I was just staring at my slides, but yeah, by all means, interrupt. Anyway, I'm almost done. So, you know, there's some key takeaways. One, the deployment of release engineering is non-trivial. We sort of think about it as an afterthought. We thought about it as a forethought as part of this project, and it's really starting to enable new things, right? And in particular, it dramatically reduces the time to science, right? You know, by the time you can talk to your developer about this, they built it, and that I think has value in this community. It's not that it supplants things; it's that it can accelerate things. But that's because it isn't, at least in my group, it isn't a bunch of graduate students and postdocs putting together infrastructure that then is very difficult to maintain and share and repurpose. This can be repurposed very, very quickly. And if that's done in a way that maintains its integrity, I think that's a real plus. Okay, I'll stop there and say thanks. It's always important to show the people on the left-hand side of the screen because we will be working for them at Google, Microsoft, Amazon, Facebook, or LinkedIn sometime in the future. So it's good to get to know them while they're young and to kiss up to them now. This work is done by myself and a collaborator, Professor Chandra Prince at UCSB in the Race Lab. I'll stop there. And I'm sorry I did not catch your question earlier. Please, by all means, ask it.
You're muted, Leo.
Oh, I didn't realize that was my cue. So some of these, this might be something that goes better with the tomorrow's session because it might be a more technical question, but I'm just trying to understand the like what's the secret sauce in the Hopskotch client. It looks like it's a pretty thin wrapper around this other package called ADC streaming, and like what is the relationship of those two projects, and why do I need Hopskotch instead of one of the sort of other handful of major Python Kafka client libraries?
Right. I don't know the answer to that in full. Part of it is that it's integrated with IAM so that you get the what's the word? The access control and identity management integration that you're going to need to do these kinds of things. And these other things maybe as well. The other thing is that it is part of SCiMMA. So the Hopskotch API was designed very much with major stakeholders for SCiMMA in mind. LSST, ZTF, IceCube, somebody else help me. But
LIGO.
But the so LIGO, thank you. Yeah, LIGO. Again, sorry. And so, you know, it very well might be that we could have eviscerated some other Python wrapper to a pub subsystem to get the level of customization for that project. And then for sure, that's the motivation. But it seemed more straightforward and cleaner, particularly with respect to the idea that there are disparate stakeholders to go through an agile development effort to produce this SCiMMA interface, which was technology agnostic. So you can remove the Kafka and still have Hopskotch, as we will do with.
I'm sorry. I mean, looking at the, I mean, it looks like the statements you just made apply to ADC streaming rather than Hopskotch.
So Mario's
like,
sorry.
Yeah.
Sorry, go ahead.
Well,
yeah.
it's,
So if I can add a little bit to that about the kind of technical layering and the decisions. So you should think of ADC streaming as Hopskotch basically as being part of the same package and developed by this group by SCiMMA. So the reason why we split them up, why we have them in two pieces, and one is even in a different GitHub organization, is because at that level, it's possible to share them with, say, ZTF or LSST or other projects that don't have a couple of specific things that are specific to perhaps us, SCiMMA. And as we're developing, we're kind of revisiting whether those two layers are actually necessary, or where we're going to just squish everything into one thing that's going to be called Hopskotch. So from the point of view of kind of using these libraries right now, I would worry about kind of those two layers because they may end up being one, just depending on where this prototype takes us. Does that answer part of your question? Because I have a second part answer as well.
I think so, but then I'm also wondering, as to why I need the Hop client or ADC streaming, and you say that it's because it integrates the identity and the identity and access management component. It seems at least that the Kafka Python package has at some sort of OAuth support built into it. I mean, is it simple? Is it just that is Kafka Python? Is it just that is it just that Hopskotch provides these abilities on top of the the Confluent client, which is more performant than Kafka Python?
Yeah, so I think you're on the right track there. So there are a couple of reasons for this library. You mentioned that it seems like a thin wrapper over effectively Confluent client, and that is true, and that's by intent. The reason for that thin, so you could, if you wanted to plug into the Kafka, any of the Kafka brokers, you could pick up either Kafka Python or Confluent's Python libraries and go do that directly. What Hopskotch adds to this are two things. One is, if you ever try to work with Confluent clients, Confluent's Python libraries, they're effectively a direct translation of how it's done in Java. And you can tell they're not very Pythonic in how it works, and they're not very pleasant to work with. So SCiMMA's or Hopskotch wraps all of this in a very kind of natural Python interface, so that your graduate student or your typical science programmer can easily get started with this and integrate it. So that was one of the reasons why we wanted why we had to add that layer, because we've used it internally for LSST and ZTF directly, Confluent client libraries, and it just wasn't pleasant. We ended up building these kinds of layers ourselves anyway. And the second reason is Kafka is currently the best system to use. It's not clear how it's going to evolve over the next couple of years. For certain areas, like Rich mentioned, you cannot directly use Kafka, but these kinds of concepts, or the API that Hopskotch is providing, is fairly straightforward to map to different queuing systems. So we can do, and what we're looking at doing is adding support for additional backends to Hopskotch. So you'll be able to connect to, say, to a BTP stream if you want to access virtual, via events, by simply specifying, rather than your URL being Kafka://something, being BTP://something. And from the point of view of the rest of your client code, they don't see the actual messaging system, messaging bus underneath. They don't see any of those details. So that's
if I could,
that you're getting here.
If I could jump in too, if you decide that you want, to go to AWS or Google or whatever, Kafka is probably not the right answer, right? They have very reliable, much cheaper message delivering systems that can be used in place of Kafka. You'd like not to change that API. Now I know about ADC, but for sure, the pub sub piece of it, in that very, very abstract way, is the connection point.
So kind of bottom line is, yes, you could go straight to Kafka and build your thing for Kafka, but then in effect you're going to find yourself rebuilding a lot of the things that already exist in Hop or Hopskotch that we try to that kind of accumulate a couple of years of experience with using Kafka and some thought about how we make this more future-proof.
Yeah, that's a really full answer, and these are all the issues that Mario and Rich brought up that we considered when we came up with the basic architecture. So we're nearing the run out of time, and I see Patrick's got his hand up. So Patrick can have the last word in today's session.
Fantastic. I was going to just say one little thing about the question that Leo brought up and how to think about it. When we do this, I think Mario gave a very detailed answer, building on what Richard already explained about why we chose this path, and I personally think it's a good one. But when we Hopskotch is a service with a client, and we're building the client so that in principle we can have users continue to use that API, but we could change the nature of the service. So that's the reason we made the choice. But of course, I think, Leo, for expert programmers and very skilled developers like yourself, you might choose for a given application on a given timescale to actually go direct to the Kafka client yourself, or the Kafka code yourself. And that should be I don't want to say we don't want to encourage that, because then that leaves us with a situation whereby we get forced to freeze the central service in some ways. But on the other hand, we don't want to discourage it either. The goal will be to, over a certain period of time, have people approach these things the way that is most useful to them. So
yeah, that's a very good point. Does that answer your question there?
Mostly. I think I'm still a little fuzzy on the distinction between SCiMMA, or sorry, SCiMMA, Astronomy Commons, and Genesis. But
I think that's a valid criticism and point, and we need to clarify that internally as well. But what I would advise right now is to focus on Hopskotch, and we'll provide some clarification of what these layers that are meant to be hidden are kind of supposed to be.
Okay, Patrick, is your hand up? Is still up, or did you have something you wanted to say? Oh, no. Okay, so only 3 minutes late. We'll wrap up here for today. Tomorrow we have the technical session on the IAM system, and I hope we'll see you then. And then on Thursday we have the Hopskotch demo and walkthrough, where we can actually sort of look at how you use and extend the Hopskotch client. So thanks to everyone for attending, and I hope this has been fruitful. Please do send us feedback, and we will be sending you a brief survey after the workshop is completed, so you can give us some more feedback. Thank you very much, everyone. Thanks to the speakers in particular.
thank you, everyone. Talk to you guys soon.
Bye now.
Bye-bye.
Bye-bye.